I want to introduce the, pretty much I will say, if there's one person that is in a serious way responsible for my being here, our Dean of Sciences, Dave Coates.
Thanks, Stefan. It's my great pleasure to be here today and to attend many of these talks. It's a fantastic symposium. Thank you all for attending. And it's my particular pleasure now to introduce the next speaker, David Spergel, who is the Charles Young Professor of Astronomy at Princeton and also the chair of the physics of Astrophysical Sciences at Princeton. And actually, I can relate to this in many ways. He did his undergraduate degree at Princeton. I did my undergrad at Dartmouth and then came back onto the faculty at Dartmouth, and so I can understand that appeal. He got his bachelor's at Princeton in 1982, and then 3 years later, his PhD at Harvard. His biography goes on quite extensively. There's a lot of impressive awards that I won't be able to name all of them. For example, he had the MacArthur Fellowship in 2001. He was elected this year to the American Academy of Arts and Sciences. He is part of the new Princeton Center for Theoretical Science and is a co-founder of the Institute for Physics and Mathematics of the Universe in Tokyo. And he currently chairs the National Academy of Sciences Committee on Astronomy and Astrophysics. So he gets around. His interests range from the search for planets around nearby stars to the shape of the universe itself. And he's working now with others to develop technologies that may enable the direct imaging of Earth-like planets. We have evidence, increasingly extensive evidence on the existence of Earth-like planets, but nobody's ever actually seen one. And so it's pretty cool, I think, that he's working on ways to actually see them. So with that, it's my pleasure to introduce David Spergel.
Thank you. I want to begin by thanking all the folks here at Dartmouth who've made this very interesting meeting possible, and by congratulating Stefan on starting here as the EEJS professor. I think it's a very exciting opportunity, and we're all looking forward to coming back and visiting you here over the years.
You don't have to go.
And, mentioned the American Academy of Arts and Sciences. One of the neat things is next week I'll be inducted, and the two of the people who are inducted with me include Mel Brooks and Clint Eastwood, and I'm bringing a chair. So I want to start, there's a lot of students in the audience. When you give a talk like this, sort of looking at where your field is, it's fun to step back and say, well, where was this field when I was a student? And when I first took my first cosmology course, there are a bunch of questions that we really didn't know the answer to. How old is the universe? Could have been 10 billion years old, 20 billion years old. We knew it was older than the Earth, but beyond that, there was a factor 2 uncertainty in the age of the universe. How much stuff is there in the universe? There we had more like a factor 10 uncertainty. Where do galaxies come from? What's the universe shape? These were all questions we didn't know the answer to. And to sort of summarize, in a sense, where we've gone, these are now questions we can give pretty detailed quantitative answers to. The universe is now, we believe, 13.7 billion years old since the Big Bang. And that's something we know to about 1%. While we don't know what the dark matter and the dark energy is, we do know how much stuff there's there. And we have a pretty good idea about the overall geometry or shape of the universe and a theory for how galaxies formed. And to begin with the conclusion of the talk, today we have a cosmological model with 5 basic parameters: the density of atoms, the density of matter, how old the universe is, how lumpy it is, and how that lumpiness varies with scale. With those 5 numbers, each of which I know to a couple %, we can describe all of our observations in cosmology and in astronomy of large scales and properties of the universe. That's pretty good, right? That's what you want to do in science, is to have a simple theory that fits lots of data. The problem is, while it's simple, it's really strange. Atoms make up less than 5% of the universe. And we have given names to the other 95%. But just because we give them a name doesn't mean we know what it is. In fact, I think one of the great mysteries of physics is trying to figure out what the dark matter is and what's going on with the dark energy. And I'll come to that, but back to those subjects as we go on the talk. In order to describe how we got to this picture, I have to first teach you a few key ideas in special relativity and general relativity. But don't worry, these are easy. They'll take less than 5 minutes. All right, special relativity. The key idea you need to know for special relativity is light travels at a finite speed. That means when you look out in space, you look back in time. It takes a few nanoseconds for light to get from Stefan to me. So I see him as he was a few nanoseconds ago. I don't see him as he is right now. Now, Stefan hasn't changed that much over the last few nanoseconds, so it probably hasn't changed that much since. The further out we go in space, the further back we look in time. So we sit here in Hanover, we look out and we look out towards Mars, and it takes light, a finite time to get to Mars, so you're communicating with the Curiosity rover. There's a real delay, right? You send a signal, time it comes back and told you've done that, it takes like of order 20 seconds. Sorry, of order 20 minutes. 20 minutes, sorry. That's a big effect. You actually want to have a lot of autonomy for the robot, because lots of things can happen. The Martians can come over and turn the Curiosity upside down before we have time to respond. The further out you go in space, the further back in time. The nearest stars are about 4 light years away. What does that mean? That's a unit of distance. A lot of times in science fiction shows, it really bugs me when they say, oh, that happened 4 light years ago. No. 4 light years is distance. It's how far light goes in a year is 1 light year. So if we see the nearby stars as they were 4 years ago. Further out you go, the further back. If you were orbiting one of these planets that people are discovering now around, say, a star that was 20 light years away, you'd be seeing us as we were 20 years ago. You'd see me with a full head of hair. The further back you go in space, the further back you go in time. So you'll hear about the Hubble telescope discovering some galaxy that was, we see it as it was 13 billion years ago. We're seeing galaxies so far away that we're seeing them, relatively close to the beginning of the universe. When we look out, the further out we look, the further back we go in time. All right, so you now know special relativity. Good. Now, in order to talk about the Big Bang Theory, and when I talk about the Big Bang Theory, I'm not talking about the TV show, though one of my colleagues likes to claim that its view of Caltech is not a comedy, it's a documentary. The Big Bang Theory really rests on 2 pillars. One is general relativity. And general relativity, as my academic great-grandfather, Johnny Wheeler, taught, consists of 2 ideas. Matter tells space how to curve, and the curvature of space tells matter and light how to move. So once I specify how matter is distributed, that tells me about the curvature of space. And that's all people are pretty comfortable with. The thing that I think people struggle with when they hear about the Big Bang Theory, and the thing that comes out of it, which is to say the universe is expanding. I actually don't like the name the Big Bang Theory. It was invented by Fred Hoyle, who was an opponent of the Big Bang theory. He liked the steady-state cosmology. I think a better name for it is the expanding universe theory, because what it tells us is the universe is expanding, getting less dense with time, and since it's filled with this hot radiation, getting cooler with time. And I think of it as describing the history of the universe since the first few moments. There's a very interesting question. Lee raised some of these issues. Robert raised some of these issues of what happens earlier on. But I think if I like to start with the universe, what we see today, and run it back in time. So if the universe is expanding going forward in time, it's contracting going back in time. When we hear the universe is expanding, the first question many people ask, and some of you are probably thinking this now, what is it expanding into? And that's because you're thinking about space as absolute. That's, you know, it's like a balloon that's expanding in this room. It's expanding into the space around it. The way I like to think about relativity is space is not absolute. Space is relative. Space is only defined in the relationships between objects. So we're not expanding into anything. Things are getting just further apart. Or if you want to think about it expanding into something, think about it expanding into the future. And the image I have when I think about the universe's expansion is I can't think about 4 dimensions, so I think about 3. I ignore one dimension of space, so I imagine that we're all living on the surface of a big ball, and we're ants, and all the galaxies are ants on the big ball. And as the universe expands, it's expanding into the future. So that balloon is getting bigger. And the radial direction is time. The radius of the balloon is time. So as the universe expands, the ants on the balloon get further apart. And that's the expansion of the universe, and the ants getting further and further apart. And as you go further into the future, the ball gets bigger and bigger. We run that back in time. The universe gets denser and denser, hotter and hotter. And the moment of the Big Bang is when I shrink that balloon down to 0. Okay. So here's history of our universe. Look, here we are today, looking back in time at stars and galaxies forming. Keep in mind, the age of the Earth is kind of interesting on this, right? The Earth's about 4.5 billion years old. So the age of the Earth is about 1/3 of the age of the universe. So we're relatively recent, but in the grand scheme of things, we kind of show up, when the Earth forms, shows up in this picture. Our solar system forms. Go further back in time. A lot of what I'm going to talk about today is the microwave background, which is the leftover heat from the Big Bang. And most of what we see in the microwave background is what the universe looked like about 400,000 years after the Big Bang. And I'll talk about some results from our space observations with the WMAP and some measurements we've been making from the ground. So first, let me begin by talking about WMAP. That stands for the Wilkinson Microwave Anisotropy Probe. Wilkinson's easy. That's my late colleague Dave Wilkinson, who played a pivotal role in experimental cosmology. And after he died, NASA generously let us name the satellite after him. Microwave, that's the radiation we're looking at. And it's just like your microwave oven. It's that wavelength of radiation. Anisotropy is a word that many people struggle with. I know when I get introduced, people often can't pronounce it. And it just means how things vary across the sky. Isotropic means the same everywhere on the sky. Anisotropic means it varies from place to place. So all that says is we're looking at how things vary. And this just shows where the satellite goes in order to be in an environment that's very clean to observe the leftover heat from the Big Bang. We actually go out at a distance about 4 times the distance of the moon. And we're out there, we were out there in space, orbiting, taking pictures of this leftover heat. So when we look out in space, we look back in time. As we look back in time, the universe gets hotter and hotter. How hot the universe is relative to today is one way of thinking about redshift. You hear astronomers talk about redshift. So when we get to a redshift of 1,000, that's when the universe was 1,000 times hotter than it is today. 10,000 is when it's 10,000 times hotter. So that going this way, the universe is getting hotter and denser, and this plot shows how density behaves with time. As the universe gets hotter, it goes from being made up of neutral hydrogen to ionized hydrogen. Neutral hydrogen is transparent to radiation, so light can travel freely through it, or microwave light. Ionized hydrogen, electrons and protons, the radiation interacts with the electrons. So it acts like a dense cloud. So over here, it's like those of you who are up, was up running in the morning, it's a little foggy. Dense fog back here. We can't see through it. As we look out in space back in time, we see back to the moment or the period of time when the universe made this transition from being neutral to being ionized. So our satellite maps what the universe looked like back then. So this cosmic background radiation, if we had eyes that could see in the microwave, would look more like this orange picture. It's actually very uniform at a temperature of about 2.7 degrees. You have to look with very high sensitivity, and this is the image from the COBE satellite, which was WMAP's predecessor, and it made the first detections of variations in the microwave background, variations about 1 part in 100,000. And our goal was to try to look at that in more detail to be able to determine things like what's the shape, what's the geometry of the universe. Since you're all general relativists now, you know that the amount of matter determines the geometry. So you've got a lot of matter, it's going to curve space a lot. Space will be positively curved, closed geometry. That means when we look at these fluctuations back then, we actually know how big the fluctuation should be. The characteristic size is how far light can travel in the 400,000 years. So nature's kind of holding up a ruler for us that's 400,000 light years across. And if the universe was closed, those spots would look very big because the path light would take would be different. The density of the universe was low, the spots would be small. If the density of the universe was just right, so that the total energy of the universe was 0, that the energy in expansion equals the energy in mutual attraction, which is negative, then the spots would be about a degree. So those are the kinds of things we want to measure by making a precision measurement to the sky. So we sent the satellite up. It was really fun. We went down to the Cape, put it on a big Delta rocket, launched it into space, and I actually did go to Disney World afterwards. So here's our satellite. Oops. There's our satellite. Oh, don't want to see it, right? It's spinning in space. There you go. Just don't have to hit. And it's out there spinning in space. It's measuring these tiny fluctuations. And the way we try to make these measurements to high precision is we make a differential measurement. A very good experimental trick is if you want to measure something to very high accuracy, don't make an absolute measurement. Do it differentially. So if I brought two of you down who were both, one's 5'8", one's 5'9", and I want to measure who's taller, if I take a ruler and try to measure it with those 12-inch rulers we got in elementary school, that's hard. On the other hand, if I put you back to back and I put a ruler on your head, it's easy to see if people are back to back who's taller. That's a differential measurement. And if you make a careful differential measurement and you do things like, we want to make sure this ruler's not warped, so we're going to flip it around lots of times. And that's what we do with the spinning satellite. We have two different points we look at any given time. We measure the temperature difference. We spin around. A minute later, measure the difference again, reversed. You can make a very accurate map of the sky. and that's what the satellite does. And these are our maps of the sky. We map them at different frequencies. This is like seeing what the intensity looks like in how much red light there is in different parts of the sky, how much yellow light, how much green light, except for at radio frequencies. So we're seeing how much energy emission are we getting at 22 gigahertz, 30 gigahertz, and so on. And this is a map is like looking at a globe where you take the sphere and project it on the plane, right? This is showing the sky around us. And the first thing you notice if you look at this picture is that big, bright red thing across the sky. That's the galaxy. That's dust and electrons in our own galaxy, the Milky Way. That's not what we're interested in. That's stuff that's been traveling towards us for about 10,000 years. Boring. You know, we're interested in this blue and yellow stuff on the bottom and the top. That's the stuff that's been traveling towards us for 13.7 billion years. So we take data at many different frequencies, 5 in our case. As we go up in frequency, the galactic emission gets less, and we know how this galactic emission varies with frequency. So what we do is we try to make our best map combining all the frequencies and try to remove the contamination from our own galaxy and from quasars and nearby galaxies. And this is our picture of what the universe looked like 13.7 billion years ago. And this is a really handy picture to have because it can tell us a lot about the properties of the universe. We can count up and see what's the number of spots we see on the sky, how big they are, how the fluctuations vary with scale. So I can ask, you know, how lumpy is this map at the 1 degree scale, the 5 degree scale, the 10 degree scale? Do I see equal numbers of hot spots and cold spots? Lee mentioned the possibility of looking for non-Gaussianity. One form of non-Gaussianity would be we have more really bright hot spots than cold spots. That would be a non-Gaussian fluctuation. And that would be very interesting. Had we seen that, that would have told us that there's something beyond our current simplest theory. As Lee pointed out, the interpretation of that's more difficult, but that's the kind of thing you can look at that would tell us something new from this data. Now, when you look at data like this, if you look carefully, you'll start noticing patterns like this. You'll notice the letters SH. I first noticed this, actually my colleague Lyman Page and I were sitting at a big conference. Stephen Hawking was speaking. This was at UC Davis in 2003. Lyman turned to me, Lyman designed most of the instrument, and said, did they put up the letters SH as a joke? Right? Because of what his students put there? And we looked at our data. No, it's there in the data. This may be telling us something profound. My own theory is that the galactic emission over here to the right is a bit stronger. Perhaps we've lost some information when we removed it. We're missing the letters I and T. When the initial conditions were created, they realized there was a mistake made and more likely, I think this actually represents evolution. We've been selected to find patterns, and it's those of us whose ancestors, you know, they look in the woods, and 9 times out of 10 when they jump because they thought there was a tiger, they were wrong. But 1 time out of 10 they were right. So it's better to err on jumping when you see something. And the people who didn't jump at all when they saw something in the woods, they're not our ancestors. They were eaten. So how do we take what we do with data like this? Well, we try to quantify what's going on with the fluctuations. We measure how lumpy it is as a function of scale. And this plot here shows the points, the amplitude of the fluctuations as a function of angle. And the conventional way we do it, spherical harmonics, for those of you who are more expert, the units we use are 180 over the angle. So that at 10, we're measuring how lumpy things are smoothed on the 18-degree scale, the 1-degree scale at about 200, the 10th of a degree scale when we get out to L of 2000. So we're just looking at lumpiness as a function of scale. And you'll notice there's a really regular pattern you see. And that regular pattern is set by the fact that what we're looking at are sound waves in the early universe, and that the amplitude of the signal depends on how the sound waves behave. So the spacing between the peaks depends on what the universe is made of. You have more atoms, that changes the spacing between peaks, so we measure that. The position of the peaks depends on the distance from here to the surface. That's how we know the universe is 13.7 billion years old. If the universe was older, the peaks would shift to the right. Younger, they'd shift to the left. The relative amplitude of peaks depends on the composition of the universe, because gravity matters. The amount of matter in the universe determines, particularly dark matter, the amplitude of that third peak in particular. So by seeing how, if there was more matter in the universe, that peak would be higher. So you can look at this data, and it's all just sound waves in the early universe. It really is fundamentally, it's freshman physics. It would take 1 or 2 fresh lectures for a freshman class to get it. But we can work all that through and see what we predict for our simplest model. And we find with this simple model with 5 parameters, we predict that red curve. And that's a pretty good fit to the data. And we look at the properties of the fluctuations. The universe turns out to be remarkably simple. That whole map, I only need 5 numbers to describe it. The fluctuations are what we call Gaussian. So this is the number of hot spots versus temperature as smoothed on the 4-degree scale, the 1-degree scale, and the 1/4 degree scale. The black histogram is our data. The red curve is the Gaussian curve, and it has 1 parameter, the width. So once I specify that 1 parameter, that red curve is completely predictive. And you can see it's a very good fit to that black data. We don't have more hot spots than cold spots. They're really basically equal numbers. The universe turns out to be remarkably simple. We don't see any evidence for interaction. We don't see any evidence that the universe is finite. We look for these things, and so far, it seems very simple. So we now have the universe's baby picture. We know what it looks like 400,000 years after the Big Bang. So we can then evolve it forward in time. And for that purpose, I've selected 3 randomly chosen babies and evolved them forward in time to about, this is about 8 years ago. And then that's what the universe would look like, about when the Earth formed. And we can then compare them to our observations then. And we could then evolve it even further forward in time. Oops, you don't really care, but there's a picture of my kids skiing. And that's further forward in time. And this is what we do with our models. We take the initial conditions. We put them in a big computer simulation. We evolve that computer simulation forward in time, starting with the initial conditions based on what we see in the microwave background. To go to Lee's talk, this is sort of classical physics in a sense. You're specifying things not in the very first moments, but 400,000 years after the Big Bang. That sets our initial conditions. The laws of physics we use here are general relativity. You're all relativists. It's straightforward to do. And we evolve it forward. You see structure emerge. And we then compare the structure we see, how lumpy that is today in the models, or how lumpy it was at the time the Earth formed, and we compare it to our observations and see what we see. And to do that, you need to see where the galaxies are. And one of the efforts to do this is the Sloan Digital Sky Survey. This is my colleague Jim Gunn who led the survey. And here's some work by one of my thesis students, Beth Reed, where she took some of the data that was collected and measured the lumpiness versus scale. And the black curve is an extrapolation from our data. And those are the points. In this plot, don't worry about the axes, but just lumpiness versus scale. And it just shows we can match the properties of today's universe running it forward in time. That says that our model has the right ingredients. And in fact, as we look at all the different ways we can look at the universe, so in cosmology, how fast the universe is expanding, we do that by measuring the Hubble constant. It's one of the things the Hubble telescope did. The age of the universe, we can look at how old stars are. The properties of clusters, and I'll show some cluster data later. The abundances of the deuterium and helium produced in the universe. How much lensing we see of distant galaxies. The properties of distant gas clouds seen toward quasars. Supernova, which are these powerful explosions we see through the universe. And this is the supernova data. For example, this plotter is a function of redshift. Remember, that's how hot the universe is, how far away we look, versus the brightness of the supernova. If there was no dark energy, the curve would look like the dashed line at best. What we predict from our data is the solid line. Those points are the points from the supernova. You can see our data, the model that fits our data, fits that quite well. In fact, you know, I've given versions of this talk in Stockholm, and it's one of the things that can help convince the folks in Stockholm to give the Nobel Prize this past year to Rees, Schmidt, and Perlmutter, shown here smiling. And what they all did, and this is the strongest evidence we really have that we have this dark energy, the universe is accelerating. They looked at distant galaxies. They then came back a bit later. Notice when they took data in those distant galaxies, these bright arrows appeared. And the bright arrows pointed to these exploding stars that were so powerful that they're as bright as the galaxy. We know how bright those stars are intrinsically, these explosions called supernovae. We look at how bright they are. We look at that brightness versus distance. And that's another way of measuring the basic properties of the universe. And all these pieces fit together. Here's another way of seeing this. The same sound waves. This is a big recent data from the big, more recent Sloan survey, version of the Sloan survey. This is actually led by a guy named Dan Eisenstein. Dan took his junior year, took cosmology from me. And it's kind of cool when there are people who you first taught them as undergraduates are now leading major projects that are finding evidence for things like the existence of dark energy. And you can see this plot below, those same sound waves that we saw in the early universe that made those fluctuation patterns, Dan and his colleagues are finding in the large-scale distribution of galaxies nearby. We're seeing that same imprint. And the position and height of those peaks are bang on what the simple model predicts. So you take what fits the data we have from space, predict what Dan's group should see, and it fits very nicely. Let me just skip through clusters. This is fun. There's a list of all the parameters measured in all the different ways. And it's a real eye test, and you should just see the numbers all look about the same. So how do we push the model further? You want to test it. So this is a plot of how lumpy it is versus scale. The black points are the data. But our theory predicts what you should see on even smaller scales. So you want to go test that. So we go and build a even more sensitive small-scale experiment. In our case, we went to Chile, to the Atacama Desert, which is very cold and dry. Our colleagues went to the South Pole, and there's a very similar experiment at the South Pole, also mapping the sky. And we look at this microwave background on smaller patches in the whole sky, but at much higher sensitivity and higher resolution. And here's a Google sky image of our telescope. Because it's inside a ground screen, we can't see what it looks like from above, but Google can. Google sky images are pretty impressive. You can look at I know we can look at our house, and I can count the number of skylights in my house. Google Sky knows there's a skylight over our bathroom. You guys know everything. And so we're zooming in and looking at these fluctuations on smaller scales. This is what our data actually looks like. Actually, we turn down the light just a little bit. You can actually see, this is sort of nice, because you see a bit of the messiness of real data. You'll see these bright little sources, that little dot. That's a big radio source. We have to mask that. And towards the bottom and the top, you see stripes. That's the Earth's atmosphere. Those are regions where we haven't mapped it often enough, because we map it more in the center, and we're left with noise from the atmosphere that leaves streaking. You have to throw that out. You're trying to measure things that are fluctuations at the level of a few millionths of a degree. The Earth's atmosphere is a lot hotter than that, and you have to deal with that. And we focus, and we see actually these little black spots are clusters casting shadows. And one of the fun things we do, I'll show you 1 or 2 images of the clusters we discover. But most importantly, we look at these smaller scale fluctuations. Here's the clusters. So we see these clusters as shadows. And what's fun is you then go to your optical telescope. You know where the shadow is. You discover new clusters of galaxies. And we've discovered hundreds of new clusters. And the numbers of clusters we see and their properties are, again, consistent with our basic cosmology. And remember, I had this prediction on what the model should look like. How do? We do remarkably well. So before, our curve only went out to here. We saw those first 3 peaks in the sound waves. Now, we see about 8 peaks. And the amplitude of those sound waves, how they're propagating, how the universe behaves when you hit it and bang it and let it shake a bit, it's very consistent. So this is, kind of classically how we do science, right? You have a model, fits the data, predict more sensitive, make predictions. You go test it. It's holding up really well, and these are 2 independent experiments. The red points are from measurements made in the group in the South Pole. The blue points are our measurements, completely independent, consistent story. So this is great. The good news is we have a standard model. All the pieces fit together. We know what's going on. Well, it's not quite true. The glass is either half full, half empty. Atoms make up only 5% of the universe. We don't know what the dark matter is. We don't know what the dark energy is. We don't really understand where the fluctuations came from. We have interesting ideas, but we don't really know. So let me end by asking 3 questions. What's the dark matter? Is it new particles from supersymmetry? Those of you who are fortunate enough to hear Jim's talk yesterday, you heard a bit about supersymmetry. One of its really neat predictions is it offers a way of explaining what the dark matter is. There's the lightest particle predicted by supersymmetry. Could be stable, could be the dark matter. And what's very exciting about that possibility is it's one that we might know what the answer to soon. This big collider in Geneva could see it. We might see it in underground searches looking for dark matter. We might see its astrophysical signature. So we actually might know what the dark matter is soon. Or it could be something very different. It could be black holes. It could be another type of particle called axions, or maybe something we haven't figured out yet. Mentioned the universe seems to be accelerating today. It's actually very strange. The universe is behaving, and that's what the supernova data is showing, that's what our data is showing, as if you threw a ball up, instead of gravity making it fall back down, it kept accelerating. It started accelerating and started moving faster. So this expansion of the universe, you'd expect to slow down from gravity. But instead of slowing down, it's accelerating. It's very weird. We don't know whether this is due to the fact that general relativity, which is what we're applying on these large scales, is breaking down, or whether it's being driven by energy associated with empty space that we call vacuum energy, or whether it's being driven by some new physics entirely. And Stefan, I will get to that paper draft on our ideas on this new physics. But life is busy. Too many things to do. One of the intriguing things we're seeing is we see this pattern of fluctuations. And this pattern of fluctuations we see are consistent with this idea of inflation that Robert talked about. And this inflationary model has some very attractive features in it. If you go back and look at this inflationary model and what it predicted in the 1980s, it predicted those fluctuations should be Gaussian. It predicted the amplitude should be about the same on all scales. It predicted that they should be what we call adiabatic, which means when I have more atoms, I have more dark matter, I have more radiation. And when I have less of everything. It predicted the basic properties of those fluctuations. It is one of the bases we use for computing those beautiful curves that fit the data so nicely. So observationally, it seems to be doing really well. The problem is, as we started thinking about its theoretical underpinnings, there's a lot of problems. We don't understand where the initial conditions come from in the model. We don't understand, in order to make inflation work, you have to tune all these things in the model very, very accurately. We don't know why we have to do that. We can make it work by tuning everything, but it seems like an artificial construction in some ways. There's lots of problems. The model tends to like to run off, and it tends to want to predict a universe that keeps inflating forever, doesn't stop. So my own feeling is this, we do seem to see evidence that the universe accelerated in the past. It's happening now. It probably happened then. I think our theoretical understanding of it is at an early stage. Perhaps we're like the theory of quantum mechanics, where there was old quantum mechanics that explained the hydrogen atom that Niels Bohr developed. And it was a good start, but we needed something deeper. And one of the things that you've got a taste of in some of the talks today, and you'll hear some more tomorrow, is different ways we're struggling with trying to understand these kinds of questions. And there's, alternative versions we can come out. We have to get the final revision done. And while this is an area where we're asking very profound questions that cross the border sometimes between physics and philosophy, it's also an area where there are real observations that we can make. Some we're making now, some we hope to make in the next few years, that can test a lot of these ideas. So one of the things that is predicted, for example, by a lot of these inflationary models is a pattern of gravitational waves, ripples in space-time itself, that are actually predicted to leave a distinctive signature on the microwave background. And one of the kind of next generation experiments that we're thinking about and working on is trying to detect these gravitational waves. So we're not, these are models that make real predictions, and we'll be able to separate, at least falsify some of the models by these future observations. So let me conclude. And this picture of a turtle and a hare, I took in my front yard. I don't know what it symbolizes, but it was just so cool to see a turtle and a rabbit lined up, looking like they're about ready to race, that I felt I had to use it in a talk. But I tried to convey in my talk sort of two halves of the story. On one hand, we've made significant progress in understanding a lot of the properties of the universe, its composition, its age, how lumpy it was, where galaxies come from. And we have a pretty simple model in some ways that fits a host of data. And the data over the past decade has improved dramatically and will continue to improve. And as it continues to improve, well, there's two possibilities. We'll either keep fitting this model, or it'll point to something beyond that model. And I think we sort of know there's got to be more stuff out there that we haven't understood. I mean, we have a model in which atoms make up 4% of the universe, or 4.5%, and we don't know what the rest is. We're missing some important things. And we don't understand why there's more we heard about matter and antimatter. why are there more electrons in the universe than positrons, anti-electrons? We have ideas for this, but we don't know what the right theory is. So this question of, why is there the stuff that makes us up? We don't understand the atoms that well either. And while it's very exciting to me that we've seen what the universe looked like 400,000 years after the Big Bang and can extrapolate back to the first moments after the Big Bang, we're still struggling to understand what that data is telling us about the basic properties of the universe. So, for those of you who are students thinking about which way to go, and this is an area where those of us working on the field, we've solved some easy problems. And there's some really hard, interesting ones for you to solve. And you're probably going to be the ones who do it. So it's a great and very exciting time. So let me stop there.
All right, so we actually have lots of time for discussion, 10 minutes, because people have, we are going to have to head over to 104, sorry, 105 Kennedy. I'm still getting to know the campus myself, which was where we were before, but upstairs. And the next talk's also going to be pretty cool and exciting. A panel discussion and talk by Andreas Hayes Jordan and Dr. King. Now we're going to put our medical hats on.
But not yet.
But not yet.
I still have 8 minutes.
Yes, so yes, the question. And wait for the mic to get to you.
I came in late, and I wonder,
You want to pick your own people?
I came in late, and I wonder, did you earlier address the issue of whether there's something drastically wrong with general relativity and all this?
Well, I put that not, I didn't address it, I raised it as a question in a sense. The fact that we see in my conclusion that the universe is accelerating perhaps is telling us that what's going wrong is the way we're interpreting the observations. What's going wrong is the way we're applying general relativity isn't valid on those scales. Now, we can test this in different ways. General relativity makes a prediction on how distance should behave with redshift. So we can look at the supernova observations and see how they, whether the supernova data fits the model for how distance behaves with redshift. Then we can look at how structure grows. You saw that computer simulation of how the universe got lumpier with time. So we compare the lumpiness we see with time versus the theoretical prediction and see if structure's growing the way we think it grows. There are modifications of general relativity that people have come up with that make different predictions for the relationship between distance and redshift and structure growth and redshift. So far, what we see is consistent with general relativity, but one of the things we're interested in doing is improving our data and seeing if we can test that the universe is behaving as the theory predicts on those scales. And, we don't have, people have many alternative theories of gravity that to replace general relativity to explain the cosmic acceleration. I think the theories at this point, I think of them as baby aardvarks. They're beautiful to their parents, but no one else finds them theoretically compelling. That said, some of the most interesting ones have the advantage of not requiring dark energy and making new predictions. And one of the things we do is we try to make ever better measurements and measure the microwave background fluctuations, the properties of galaxies with more and more detail. And here we're helped by basically our engineering colleagues who build more sensitive detectors, bigger cameras, develop the technology to do that, and then we can make more precise measurements and test the theories. I mean, an interesting kind of philosophical discussion is, does science drive engineering, or do advances in technology drive science? And my own view is yes. Yeah.
I have a very elementary question. It's about the observational method. So this notion of the background radiation and that it would be comprised of microwaves, and those are the things that you would measure with when you got to outer space. Where did those notions come from? Why would you select microwaves as the primary signatures of the supposed origin of the universe?
So we stumbled onto it, is the history of it. So Arnold Penzias and Bob Wilson were two astronomers at Bell Labs. In the 60s, Bell Labs was supporting a lot of fundamental research, but stuff that was useful for the company. And one of the things they wanted to do was, maybe we'll use microwaves for phone communication. We should study what things look like in microwaves and map the sky. So Penzias and Wilson built a really sensitive microwave experiment. And they went out and they looked, and they were, for the company, I'm sure when they went and did the presentation for their company vice president, they said, we're doing this so when AT&T uses microwaves, we'll be ready. But as scientists, they wanted to see what was there. And they saw our galaxy coming up and down, that pattern. Remember that bright pattern you saw of red? They found that. And then they saw this uniform stuff everywhere they looked. And one of the things that made them such great scientists was they didn't ignore something they didn't understand. And they had this leftover signal, and they worked for a year trying to find the source of that leftover noise. They replaced detectors. They, famous story, there was a pigeon roosting in their telescope, and they thought that maybe it was heat from the pigeon crap. So they went and, sometimes part of science is going in there and clearing out the pigeon shit. And you go out and you clear that out. Sometimes it's metaphorical, and sometimes it's real pigeon shit. And they did that, and results stayed. And at the same time, some of my colleagues, Dickey, Jim Peebles, who are actually independently rediscovering some work done in the 50s by Alpha and Herman and Gamow, realized that if you start out with a hot Big Bang, you could explain the abundance of helium in the universe and predict this leftover radiation, and the temperature would turn out to be such that it would be in the microwave. So that's how we found out there was a hot Big Bang. And then once you saw this uniform radiation, the next step was trying to find the fluctuations. And that led to a series of experiments of increasing sensitivity as people look for the leftover fluctuations. And initially, the models predicted the fluctuation should be much brighter, because the models were based on a universe made of atoms and radiation and electrons, and protons. And it didn't assume any dark matter, and said the fluctuation should be about 10 times brighter than they should be. And in fact, I remember as a student, people hadn't discovered those fluctuations yet. And I'd go to talks on the subject, and they were boring because they were just limits on what you saw, and we slowly moved forward until the Kobe result came out, and we saw the fluctuations. And then, the ideas here have come at, if you look at their history, they've come in many different ways. So the notion of dark matter goes back to work from Zwicky. When he looked at these clusters of galaxies, he noticed the galaxies themselves were moving around so rapidly that there had to be more stuff holding it there. So he said there had to be extra matter, and he posited that in the 30s, and there was work done looking at the Andromeda galaxy in the early 30s that showed that it had it. And it was really only in the 70s when that idea got revived, as people trying to understand galaxy properties realized you needed dark matter. And this idea of a cosmological constant or vacuum energy, well, the mathematics of it goes back to Einstein. And Einstein put the term in. Einstein actually put it in for the completely wrong reason. Einstein looked at his theory of general relativity, realized it predicted the universe must be expanding or contracting. As far as Einstein knew, the universe was static. He didn't know about the work that Hubble was doing. And so he added a term to make the universe static. It's something he called his greatest mistake, because his theory actually predicted the expanding universe. But then he screwed it up. And he took the, then he learned about Hubble, he threw the term away. But that term kept coming back. So in the 50s, there were some deviations, people posited it, and then by the 90s, there was kind of growing observational evidence that would be better understood by adding a cosmological constant to the theory. It made the fit to the data better. But it was the supernova data in the late 90s that was really the turning point. I mean, it wasn't that it was a surprise, that data, but it was strong enough evidence that really swung the pendulum of intellectual opinion, and is the point where it really, the case became strong for dark energy. Yeah, right back there. Do you want to just pass the mic up? Or?
I sort of had a question that might be a little bit of a philosophical question, but in the last talk by Dr. Smolin, we were discussing the possibility that the laws of nature might have evolved over time because they can't be completely extrinsic to the system that they're part of. And so if the standard model that you're presenting can predict accurately and stay consistent with, the cosmic microwave background, and it's also relevant today, does that sort of preclude the possibility that the laws of nature evolved over time? Or
No, and in fact, the question whether the laws of nature could evolve with time is one we try to ask experimentally, observationally, extent we can. So, what we can do is we can ask 400,000 years after the Big Bang, to the point at which we're observing the microwave background, was the mass of the electron the same as it is today? Was the strength of the attraction between electrons and protons the same as it is today? And we make an estimate of what that will do. And it turns out what we can say is the laws of physics, those laws, haven't changed to a part in 10 to the 4 over that period of time. Now, the basic properties of the universe over that period of time, the universe since then has been relatively well behaved, and it's been conditions like we see in the laboratory. I think the kind of things that Lee thinks about when he's thinking about the laws changing, he's imagining it happening earlier. He's imagining it happening in the Big Bang itself. And before. So you're looking at, we do ask, but you can imagine a theory where it's changing then might predict some later changes, but doesn't have to. So we look for it. And if we saw evidence for it, that would be very interesting. And we hope to, one of the things we will do, and motivated by just these kinds of questions, is go and look and say, all right, as our data improves, do we see evidence for the laws of nature changing in time? So one of the things I find so exciting about being a cosmologist is you can take a lot of these questions that are, really very philosophical and about our beginnings and things. And some of them, you can work them to a point where there are predictions that you can test with data and go out and measure it, see what's there. Yeah. Okay.
And we have a coffee break after this, so people are invited to Harmony, where our next starting at 3:30.
Right, or most immediately, as we walk over, I will be walking after I answer this question, and happy to answer them as I walk and talk. I can do both at the same time.
I just wanted to pick at your data a little bit, the power spectrum data that you had with the really high multipole moments up to 3,000.
Yep.
So it looked like the Antarctic data, the red dots, were slightly higher than your Atacama points. Is there a reason behind that?
There's a reason behind it, and a bit of a story I didn't get into, which is when you look at the data, you have, in addition to the fluctuations we saw, you have these radio sources. You have those bright spots. And they're producing additional fluctuations on small scales. Now, the brightest ones, we just remove. But there's always dimmer ones that we can't see with our telescope. And those dimmer objects contribute fluctuations. They don't have the same, They actually have nothing to do with the microwave background. But with our data, we can't distinguish between a few radio sources and
So would you say that your data is clearer than the
no, it's
NRC?
just their version of the data. Their data is very high quality. So what we can do,
Then what
so what I didn't show, I have it here. I can show you a more complete version of the data. It might be here. So this is the version of this talk with equations. If I find the better version, more complete version of the data. No, talk. All right, I'll just graph what our data looks like. Amplitude of fluctuations versus we call L, so it's 180 degrees over angle, and our data looks like, or at least our theory looks like that, and the data basically follows that. Go up to really high L, you get a contribution that looks like that from sources. And to make life easy, I stopped the graph there, but we actually have data going up here. And we spend a lot of time trying to figure out from what we measure here what the contamination is here. And another thing we do, so I showed one frequency, we measure the sky at 2 frequencies. The experiment in the South Pole measures at 3 frequencies. How the amplitude depends on frequency. We're taking data with a European satellite called Herschel to look at the same region. We're looking at that data. We're looking at some data. These same dusty galaxies, they're kind of interesting in science. One man's annoying source is another woman's object of study. These dusty galaxies are where most of the galaxy formation and star formation in the universe are taking place. So they're really pretty interesting in and of themselves. So they become kind of really interesting objects to study, and we want to characterize that and understand that, and then see what's going on here.